Ana Maria Rey is a JILA fellow and member of the NIST Quantum Physics Division in Boulder, and she's 6 years past her most recent postdoc, so she's early in her career. Many of you will know her. Certainly the people around the world do. She operates a group with 10 graduate students and postdocs in atomic and molecular and optical physics with strong ties to condensed matter physics, quantum information, and quantum simulation. So that fits into the main strength of NIST and JILA in particular. And she's not, I will tell you that she's taken off like a rocket as a young theoretical physicist. But I don't have to pound the table because I can prove it. Just in the last year, she's been recognized with the Great Minds in STEM Award, Presidential Early Career Award for Scientists and Engineers, PCASE Award, Maria Goeppert Mayer Award. That one is actually for Early Career Women Physicists, and she received a MacArthur Fellowship. And I won't say the words genius grant. And the last two came on adjacent days. That was actually very bizarre. Because I got an email, and then the next day I got another email, and I said, well, I just got that, and no, it was a different award. So she's been recognized by people outside of NIST, and that sort of speaks for itself. These are extremely rarefied, high caliber recognition. I got 3 points that I want to make about Ana Maria. One is that a key attribute of her approach to physics is that her theory directly touches experiment. And she's one of those individuals who has communion with the experimentalists around her, and not just at NIST, but elsewhere. And not just to interpret what the data have to say, but also help guide the design of the experiment. And so this interface between experiment and theory is really important, and she's extremely effective at that. Just to give one example, you'll have seen the press releases on NIST having the world's most accurate atomic clocks, but it was based on new physics ideas pioneered by Ana Maria. And they're able to, they're stable to 1 second in 15 billion years. And people have funny reactions to that. They say, well, you know, am I really concerned about 1 second in the age of the universe? But that's not really the point. The point is that precision frequency measurements impact a lot of other technologies. GPS and technologies of the future, about sensing the Earth and so forth. And so that ability to do atomic physics at that precision is very important for technology. And the way you keep score is your clock stability. And so she's been heavily involved in studying ultracold gases and frequently simple systems, but one of her major vectors is to move into more complicated quantum mechanical systems where there are many more participants, but they have this characteristic that they to some degree are coherent, and understanding those and controlling them is actually one of the goals. But it's going beyond it's going beyond the simple BEC into coherent crystals, and it's impacting advanced materials, quantum control chemistry. And my personal view on this is that doesn't even capture why it's important. Just as the technology we use today, every single one of us, is radically different than it was 15 years ago, in 15 years, it'll be radically different again. And it'll be based on a lot of the ideas in quantum control and quantum engineering and so forth. And these are being explored now, and NIST is really a leader in that, and Ana Maria is one of our stars. So that's the broader view of the impact. Just a little bit on her background. She got her bachelor's degree at the University of the Andes in Bogota in her native Colombia, and did her graduate work at the University of Maryland with Charles Clark, who is right here in the front row and radiating his presence. And then she did a postdoc with Misha Lukin, who's another one of the bright shining stars in the theory scene. before becoming a JILA Fellow in 2008. And so just one personal note on that. If you actually are into scientific genealogy, and I'll use family relations as a metaphor right now. She worked for Charles, and Charles was a student of Ugo Fano's, and Ugo Fano was a student of Enrico Fermi, and all of those people, by the way, interacted with experiment rather than take theory off into a corner and work formally. And so that tradition shows some sort of genetic marker that is passed down through the years. The personal note is, since Charles and I were siblings, he was my kid brother, several years behind me. That means that I'm honored to introduce my academic niece, Ana Maria Rey.
Let me start by thanking Joe for the kind words and introduction. It's really a great pleasure for me to be here today, and it has been a great pleasure for me to have been all my career vinculated in some way with NIST. It's something that I value very much, and yes, it's a great honor for me, and all the examples that I received from my advisor and all the people surrounding that. They were the people who motivated my interest in experiments. So thank you very much. Today, the title of my talk is Building with Crystals of Light and Quantum Matter, from Clocks to Computers. And what I want to do today is to give you an overview of the research that has been going on in my group, and specifically focus in the very important collaboration that we have had with experimentalists at JILA and NIST. So all this research has been possible because of this very close collaboration that I enjoy very much. So I want to start by acknowledging this collaboration. So I'm going to acknowledge especially the strontium optical clock team run or directed by Yun-Ji, and also the NIST Colloquium team, Andrew Ludlow, Chris Oates, and of course the fantastic group of graduate students and postdocs involved in the experiments. And as well, I have to acknowledge a very excellent theory team, graduate students, postdocs, and now collaborators that have been priorly in my group, but for example, some of them are here now. Well, with that, this talk is going to be about cold gases. So let me start by telling you what we mean by ultra-cold. So ultra-cold atoms, if we want to define them, then we need a thermometer and we need a scale. So we know here at NIST, and Kelvin is a very good scale to define them. So if you think about what happens at room temperature, then the atoms are moving really, really fast. They are moving at a velocity of 300 meters per second. And well, certainly this is too fast to do something with them. And then if I ask you to think about something really cold, then you might start thinking about, well, maybe very, very cold could be the temperature of the outer space, 4 degree Kelvins, or the temperature when liquid helium condenses. And these temperatures really cold, certainly, 4 Kelvin, but still at these temperatures, the atoms are moving very fast, 90 meters per second. So this is not what we want. We want to really have the capability to control them. And so what we mean by ultra-cold is really something extreme, really extreme, 1,000,000 of degrees of Kelvin. So there are gases that are with 10 to the 4, 10 to the 6 particles, but at a densities that can be 5 orders of magnitude lower than what you are using here. So really, really very dilute systems. Very cold, that are 10 to the minus 8 Kelvin, that's characteristic temperature. And the key point is that at these temperatures, the atoms are moving really slow. So we are talking about centimeters per second, and this is going to be our tool to control them and manipulate them. And a box for exploring quantum mechanics. That's what we want to do, exploring quantum mechanics at the macroscopic level. So this great capability was possible thanks to very important developments in the field, and NIST has been a key contributor to that development. So the first Nobel Prize in 1997 was given because of the possibility of using laser cooling to cool down the particles. So bombarding the particles with light, with photons, we could slow them down to microkelvin temperatures, and the prize was given to Steve Chu, Mohin Tanuji, and Bill Phillips. However, this was not enough, so we wanted to be colder in order to see macroscopic quantum phenomena. And then it was achieved a few years later by Eric Cornell, Wolfram Ketterle, and Carl Wyman, where they were able to cool down particles between 10 and 100 nanokelvins and create a new state of matter, the Bose-Einstein condensate, where bosonic collapse all the atoms to the same ground state. So this, that was recognized with the Nobel Prize in 2001, opened the door for the exploration of quantum mechanics. So that's going to be one key ingredient. So we have ultra-cold matter, but in addition, if we have this matter, we should be able to manipulate them, manipulate the atoms. And one key point in my talk is going to be the idea of optical lattices or crystals of light. So the basic idea, this is a cartoon picture of that, is that we can exert force on the atoms using light. So we illuminate the atoms with laser beams, and therefore the atoms feel a force that depends on the intensity of the beams. And in particular, if you use two counterpropagating laser beams that form a standing wave, then we can trap the atoms in these potentials, and the atoms are going to be trapped at the bottom of this well. So this is 1D picture, this is a 2D cartoon. You see a neck cartoon when the atoms are trapped there. A key point that I want to focus is that we are really exploring quantum mechanics here. So the depth of these wells is so high that classically these atoms would never be able to move from one well to the other. They were frozen because the energy is much more lower than the barrier. So the only mechanism where the atoms that facilitates the motion of the atoms is quantum tunneling. So really, this is an exploration of quantum mechanics in action. Okay, so we have my atoms, we have how to manipulate them with light, but then the next question is, well, what can we do with those atoms? And one of the key ideas that I want to tell you about today is the possibility to allow us to explore quantum complexity. So I showing here some pictures of complex systems. And well, I think that my main idea here is trying to tell you, these pictures show by themselves that complexity is something that is really fascinating and useful for technological applications, for example. So the kind of complexity that we want to explore is complexity in quantum many-body systems. And I think an important quote that summarizes this type of complexity was by Phil Anderson. He was a Nobel Prize, he received the Nobel Prize in 1977, and he said, the behavior of a piece of matter is not just a sum of the behavior of its constituent particles. So that means, if I try to understand what is the behavior of few particles, like here, that's possible. This is not going to guide me or tell me anything or explain me the behavior of the many-body system, because there are concepts like quantum superposition, quantum correlations, and quantum entanglement that not does it. So the behavior of the many-body system is just correlated. It cannot be explained by just knowing what each particle is doing individually. So you can think of that. The problem is that in quantum mechanics, the number of degrees of freedom accessible in a many-body system grows exponentially with the system size. So you think it's hard to even exactly solve for more than 20 particles. It's really hard. So, and if we have to keep track to all of the possibilities, many of these degrees of freedoms to explain the behavior, then it becomes something really very complicated, very difficult. And this is at the heart of the difficulty of quantum modern science. How we are going to deal to explain strongly correlated quantum systems that, on the other hand, are the ones that experience the phenomenon that we want to model. So it can be a little bit discouraging, but then there came a very, very provocative idea by Richard Feynman. And he said, well, maybe the solution is take advantage of quantum systems by themselves. So can we use computers, when we create computers using quantum systems, So the idea of simulated physics with computers. And Richard and Feynman had two different directions, all of them, both of them connected to each other. One is the possibility of actually doing digital quantum information, right? To create this quantum machine to perform computation. This is the quantum computer, and it's based on just quantum mechanical elements. This is one possibility. This is fantastic, but it's a little bit harder than the other possibility that is kind of the analog possibility. That is, try to use one fully controllable quantum system to emulate another system that is not fully controllable but exhibit the phenomena that we want to explain. So we have our atoms, we can poke them, we can manipulate them, we can control them even dynamically during time. So the question is how we can take advantage of this controllability to do something interesting. And well, this has been a holy grail, a very big push in the AMO community, trying to really accomplish this idea. So what we are planning to do, the idea is trying to use atoms in these periodic potentials to emulate the behavior of electrons in solid state crystals. So this is the one-to-one correspondence and sounds really interesting, really appealing. Why? Because, well, there are very important possibilities that we have that condensed matter systems do not have. We have the possibility to have something that is fully controllable, no defects. So we don't have vibrations like phonons of the red because it's really created by light. It's perfect. So this is enough that we have fully control. The Hamiltonian that describes the behavior of the system is really the Hamiltonian that we write in a piece of paper. It's not approximation. It's really exactly what we expect the system is going to do. This has to be contrasted with the condensed matter world, where on the other hand, everything is very complex. You have defects, imperfections. You have a piece of material that you don't know exactly how its behavior, but you can write approximated Hamiltonians. And this is what one of the main contributions of condensed matter physics is trying to extract the most important ingredients to describe the behavior of a material. So this looks really nice. And well, this is a direction that we are exploring, although there are two concerns or two important points that need to be addressed. These are that, well, we are dealing with different systems anyway, and therefore different energy scales. So if you look at the lattice spacing, this is imposed by light, micrometer separation. Whereas if you look at what happens in crystals, the spacing is just angstrom, atomic scale. So 4 orders of magnitude different at least. Now, if you look at what we are working, we are not working with electrons, we are working with atoms. These atoms are much more massive. Again, other 4 orders of magnitude difference. And these two scales, this is what determine the energy scales of the system. Then determine the temperature that we need to reach in order to see the phenomena that we want to see. So a phenomena that happens at Kelvin temperatures in the solid state world will require to push or to decrease our temperature to nanokelvin or below. This is too cold, very cold. Even at current experiments, we are now trying to deal with this aspect, how to do and overcome this challenge. And certainly there has been progress in that direction. We are trying to overcome this very complicated challenge by following various directions. One direction is trying to develop very sophisticated cooling methods to achieve these very cold temperatures. And actually, it's very impressive, but we are improving in that direction, and there are experiments that can report kind of picokelvin temperatures, but limited experiments, but there is some progress in that direction. However, this is not the direction that I'm going to tell you about, because there are other possibilities. Which one of those? We want to explore new type of systems. Maybe the problem is that we have been focused on the systems that where we reach initially BC that are easy to manipulate, easy to deal with. But maybe we need to expand our horizon and try to look at systems that, on the other hand, are more complex. But this complexity offers other possibilities, actually, to try to reduce or relax the temperature scales required to see phenomena. And in addition, take advantage of ultra-precise tools. This is exactly what Joe was mentioning. We have the possibility to have really precise systems. And the question is, how can we take advantage of them to look at very cold phenomena, very low energy scales? So actually, in the AMO community, and in particular also at JILA and NIST, there has been a push towards this direction, and there has been various systems that have been started to explore that are more complex, like polar molecules, very excited atoms, regular atoms, magnetic atoms, trapped ions, or alkaline atoms. And this talk is going to focus on alkaline atoms. So I'm going to start telling you why I'm pushing, I think these atoms offer a great possibility for investigation. Well, let me introduce them to you. These atoms are the atoms that have 2 outer electrons, so they are in the second column of the periodic table, although there are others with similar structure like ytterbium, for example. And this talk, as is going to become clearer as I go on, is going to focus on fermionic isotopes that have nuclear spin I that is greater than 0. This is going to come later in the talk. All right, so why? Well, it has been known for a while that these atoms are ideal timekeepers. And this is based on the unique atomic structure that they have that make of these atoms perfect for atomic clocks. And if you look around the world, now there are many, many laboratories. So I'm writing here some of them, but it's not exhaustive, the list. There are many of them that are pushing and trying to build clocks made of alkaline atoms. And in particular, I want to emphasize also what was mentioned by Joe, that, well, the JILA strontium clock this year has become, or has been reported to be the best clock in the world, and is operating with the strontium atoms. So why? Well, let me start to explain what is the appeal of these atoms, why we are using them for clocks. And of course, I want to explain you very briefly the idea of the clock. So atomic clocks are the best, can provide an unrivaled definition of the second, because they are fundamentally based on the quantization of energy levels imposed by quantum mechanics. So that means that an atom has some energy levels that has the same frequency, or the spacing, the energy spacing is going to be the same here or in China, everywhere. So it's not like a man-made pendulum or something that changes whenever I am, or some astrophysical object that can change during time. No, these are universal and useful every time, everywhere. So this frequency spacing between 2 levels is what is going to determine a frequency, a time, because it's related, time and frequency are inversely related. So the idea is that I have this very well-known frequency, and well, anyway, the clock is a mechanical object. So the mechanical object that I'm going to use in this case is a laser. So it's a laser. This is kind of the pendulum of my clock, what is ticking, and I'm going to lock the ticks of my laser to my atoms because I know the frequency very well. So what I'm just going to do is a feedback loop where I can know when I have phase locked my laser to my atoms. That's the idea of the clock. That's how it works. Well, and well, if you can think, you can see since 1967, the definition of the second is based on the energy spacing of a cesium clock. So it has been certainly is recognized the utility of that. But what I want to say here also is that the cesium clock is currently not the best in the world. So we have surpassed the capability of cesium. And for that, well, I think the idea is very simple, so I'm just going to show it here. So if I ask you to see which ruler is better, well, you immediately are going to say, well, ruler B is better. And the idea is, of course, it has more ticks. Well, more ticks, higher resolution, and this is exactly the same for clocks. So in the cesium clock, the energy spacing is gigahertz. So in order to excite this transition, I need microwaves that are much more slower. The ticks is much more slower. That's what happens in an optical clock, where the energy spacing is much bigger. It's 100 terahertz, and at least 10 to the 4 times faster than microwaves. I have faster ticks, and therefore more precision in my clock. So that's very clear that, well, optical clocks would be better. So, but it's not enough. It's not the only requirement that I have to create a good clock, because any atom has excited states that can satisfy this optical transition. So I need a very stable oscillator. So my atoms have to have certain specific properties, and this is the case for alkaline atoms, where I have 2 energy levels that in my talk is going to be the ground and the excited state. And these two energy levels have a lifetime that is really, really long, more than hundreds of seconds. That means in quantum mechanics, or the time is inversely proportional to the energy resolution. So the longer I can measure, the more resolved I can see my energy. So that's the idea. So these atoms that live forever or live very long are ideal for spectroscopy. And another way to characterize that is try to think classically. If you have a pendulum and you want to quantify how good this pendulum is, you associate a quality factor that is how many ticks I have before it dance, basically. So if you try to do the analogy with the clocks, then we will have an oscillator that once set, it would sing for the entire age of the universe. So we have a quality factor larger than 10 to the 7. So that's perfect. Not enough also, because we have the atoms, but we need the laser. If the laser is very bad, then we don't gain anything by having such a nice atom. So that has been a very big push at NIST, at JILA, is try to create the best lasers. And actually, it's very impressive, the progress in lasers technology. And now we have lasers that have a quality factor larger than 10 to the 15. I mean, they remain the coherence for more than few seconds. And this is very good. So they're trying to match what the atoms are, all the quality or the advantage that you have by using the atoms. So we have these two. But that's also not enough. So what about if I have a lot of errors because something else? And if I ask you to think about what type of errors you will get immediately, then maybe you would say, well, yes, I know that if I'm moving, I'm going to have different frequency because it depends, the frequency that I see depends on my velocity. So it's going to be something not universal. And that's where optical lattice play a key role, because optical lattice have the possibility to remove Doppler shifts, that is due to motion of the atoms, by trapping very tightly the atoms. So that's another development that happened. But not enough, because if I have a trapping potential that is different for these two states, then I always also going to introduce some error. So a key point was the possibility to actually develop what is called magic wavelengths, wavelengths at which the trapping potential field by these two states is the same, is identical, removing any type of errors from the trapping potential. So this is a quick summary of why we have such good possibility with these atoms. So that's great, fantastic, but this is not also going to be the focus on the talk. the topic of the talk is a little bit more ambitious. Can we use this for more? And this is the idea. Can we use atomic clocks for exploring many-body physics? We want to use exquisite control, ultra-precise, long times to try to probe quantum magnetism and many-body physics. That's the idea. And I have a very simple movie that I want to show you, trying to convey you why this might work. So I'm going to ask you, what type of atom do you see? Imagine first that I have a clock that is not good, and I can only probe for a short time. So let's do that. Did you see the atom? Let's try to repeat it one more time. Did you see the atom? So let me use a very good clock. Let me try to use a clock where you can really probe for longer times. So, did you see the atom? So that's the idea. That's what we want to do. We want to use, even though the temperature might be high, we want to use a very good clock to give us resolution. So we want to use a clock as glasses. We want to use this clock to resolve some blurry, some complicated energy levels that we only in principle have very small energy spacing, but be able to use the resolution to see the many-body spectrum. That's the goal, and that's what we are trying to push to. And I would say we are starting to do that. It's only the starting, because actually the capabilities are immense. So for that, let me also summarize one of the key tools that is used for spectroscopy. That is the idea of Ramsey Spectroscopy. And this Ramsey Spectroscopy proposed first by Norman Ramsey. He was recognized with the Nobel Prize as well. And the idea is that, well, we have to think about the two-level system quantum mechanically. So we are going to think about these two levels as an effective spin 1/2 system. So I'm going to spin 1/2 generally has two values, -1/2 or 1/2, and I associate these two by an arrow. So I'm going to show here you a block sphere, it's called a sphere, where if my vector points down, I have the atoms in the ground state. If my vectors point up, I have the atoms in the excited state. But in principle, in quantum mechanics, I can make superpositions of these two states. So that's what I'm going to do. I'm going to first prepare my atoms in the ground state, and then have a pulse with some generated by my laser with some frequency, from some laser frequency, and this is frequency is what I want to measure. So, but I create a superposition of these two states. That means I rotate my block vector along the equatorial plane, for example. So as any magnetic moment or as a gyroscope, in the presence of a magnetic field, this is going to precess in a plane perpendicular to the magnetic field. Exactly here happens for the atoms. So what happens is that I'm going to wait some time t, where these atoms in the rotating frame of the laser are going to rotate and acquire some phase. And the phase that are going to acquire is going to be proportional to the tuning between my atomic transition and the laser. That's how I'm going to make my clock, because this is what I want to determine. So after some time, then I want to measure this phase. Phase is not easy to measure. You measure population, so I'm just going to do another pulse that transfers population, phase to population, and from that, what I'm going to see in my experiment is what is called a Ramsey fringe, an oscillation that has some phase and some amplitude. The phase is telling me information about the detuning, and the amplitude or contrast is going to tell me about the coherence, how would I have done this operation. So this type of spectroscopy is clear and it's beautiful and works very well for one atom. But the question is, what happens when you have many of them? That's what we want to address. And immediately you are going to imagine that the fact that atoms can experience the presence of the other is going to change the picture of a single atom. The interaction between the atoms is going to be key, and that was one of the biggest limitations that people face trying to use atoms for clocks. So, but for that, let me remind you that we are anyway in the quantum world, and even collisions need to be thought quantum mechanical. So if we think about collisions, then we have to think about waves. So when two atoms collide, they have an angular momentum, relative angular momentum, and this angular momentum must be quantized. So what happens is that we have a set of partial waves that measure this quantization of the angular momentum that go in increasing energy. The lowest energy case is when you have L equal to 0, this angular momentum equal to 0, and this is characterized by being spherically symmetric. That means the particles, the wave function involved in this type of collision must be spatially symmetric. The next possibility is L equal to 1, where you need to be antisymmetric. The parity goes like minus L to the minus 1. So this is antisymmetric. And however, there is a big difference between these two. This is the distance between the atoms, and this is the centrifugal barrier, so it's angular momentum. And there is a centrifugal barrier that builds up when you have L larger than 0. So this means that in order to collide, to approach each other, the atoms see a big barrier that suppresses the collisions. So for now, we have to combine this idea with the idea of quantum statistics that start to play a very important role when we explore quantum physics. So in particular, the Pauli exclusion principle forbids to have two fermions occupying the same quantum states. That means if I have identical fermions, the wave function must be antisymmetric, and therefore I cannot collide in this way. It's forbidden by Pauli statistics. The only collision that I can have is this type of collisions for identical fermions, and this is one of the sources that were planned to use to avoid collisions. In this type of collisions, I have a barrier, so let's use identical fermions. That's the way to go. Well, yes, certainly. So this is the way that clocks currently operate with an optical lattice. They have a very deep optical lattice potential. You can see the optical lattice along the z direction that fragments the cloud in an array of disc-shaped potential. So we have disc-shaped potentials where the atoms are frozen along this direction, not that frozen along this other transverse direction. But I have many atoms, so now instead of thinking about a spin 1/2 particle, I have to think about a spin n half particles, because I have n particles times 1/2. So ideally, that's what I want my clock to work. Then each atom is going to precess at the same frequency, and I have a very large signal-to-noise summation, and that's why neutral atom clocks that operate with many atoms, in principle, had the potential to surpass the precision of trapped ions clocks that operated with a single ion. So that was the goal, or that's one of the main appeals for neutral atom clocks. However, as I say, there are collisions, and immediately after the experiments were done, they found that these degrade the precision of the clock substantially. Even though they are very weak, they were contributing to the largest systematic of the clock. And well, it was a little bit of disappointing at the beginning because, well, we wanted this to work perfect, but it doesn't work. What is going on? Well, this at the time when I was arriving to JILA, and certainly it was a very interesting possibility to me because, well, it's damaging the precision of the clock, but if they are seeing these interactions, this means that we can use the clock for something else. So that was the idea. Well, let's try to understand better what is going on, trying to use them as a tool also to prove many-body physics. And in particular, notice that the clocks operate at microkelvin temperatures. So we are not in the nanokelvin regime. We are in a different regime, but still we are using the precision of the clock to see these interactions. All right, so that's a very interesting idea that we came up with. That is, well, maybe we can really do a quantum simulator even though it's a microkelvin temperatures. So how we are going to do that? Well, one big advantage that we are going to use is that the interactions are weak. Because of this barrier, the P-wave barrier, the interactions are just of the order of hertz. And this needs to be compared with the characteristic energy scales of the kinetic energy of the atoms in the pancakes. So along the lattice direction, they are frozen, but in the other direction, in this direction, they are mobile. And actually, they are thermal. At these microkelvin temperatures, they are really a Boltzmann distribution. Remember, the energy levels are quantized. Along this transverse direction, they feel kind of a trapping potential because of the Gaussian laser beams. It's a quadratic potential. They occupy various levels. And the key idea here is that the energy spacing between the levels is 500 hertz, much more larger the single particle energy spacing than the kinetic energy. So this places us in a unique regime where collisions between these atoms cannot provide enough energy to change their energy levels. So this costs a lot of energy. So that's the idea, that we can now come up with a new type of lattice. It's a lattice in energy space. So because the atoms are really frozen in each of the levels, then it's not a lattice, the optical lattice that I have told you that we make with laser. It's a lattice that is energetically built up in the system naturally because of the weakness of the interactions. When now the quantization exists is the energy levels that I have populated my atoms. So they are frozen in each lattice side there, and the only thing that happens is that the dynamics of the spin degrees of freedom. So that's why we are building a spin simulator, because all interaction can only modify the spin, they cannot modify the motion. And that's why motion and spin gets decoupled. And even I have something that is working at microkelvin temperatures, I can only focus in spin. So that's one of the key ingredients. So second, these way atoms in each quantized levels are localized in position. So they are not localized in a given lattice site, they are really spread out. And in this basis, interactions are not local, because interactions are all local in space. One atom bump into each other when they meet, but if they're delocalized, these interactions acquire some long-range characteristics like position and momentum. They are conjugate variables. So if you know the position, you don't know the momentum and so forth. Similar. So now we have interactions that actually are long range in momentum in this energy space. This is a quite different context that we are used to. But this simplifies the physics of the treatment substantially, because instead of thinking of each atom, of each spin 1/2, now I can also use the same basis of all the atoms collective. So I have now an object that is a collective spin, that is the sum of the spin of the atoms. That's what I care of. And if I write the Hamiltonian, remember this is the Hamiltonian that I was telling you when all the atoms were ticking together. But now what I'm going to add is some guys here, some terms here that are accounting for the interaction between the atoms. So you can see its interaction terms because they are quadratic in the spin operators, so density, so interaction are proportional to the number of atoms squared. So it's this term of these terms. So these are the interaction parameters, and they are originating from P-wave interactions. So the first question is, how can I measure those? One, and how can I use them? So that's the experiment that was carried out. And, let me say that the work is a little bit more complicated because they found that atoms, even though they're very stable in the excited state when they are by themselves, that's the idea of the clock, they're very stable atoms, two atoms in the excited state nevertheless can collide and release the energy. So there is inelastic processes going on, and these are some things that we have to care about. But well, we will take care of this later. But at the moment, let's imagine we can somehow filter out these losses. And that's kind of the experiment that they did. So go back to Ramsey spectroscopy. Remember that we have two characteristic parameters to measure, the phase and the contrast, the amplitude and the phase. So let's start by the phase. The idea is that the presence of other atoms is going to modify the frequency that I'm going to measure for each individual particle. How this modification, how can I quantitatively account for this modification? And one very nice way to think about it is that mean field theory works to characterize the phase. So mean field theory means that, well, as I said, many body systems are really tricky, very complicated, and I cannot solve for them accurately. But I can imagine that I will go solve average properties. So I'm going to look for what happens to one atom, and I'm going to treat the rest as an average. It's an approximation, but in some type of observables work quite well, specifically for the phase. So if I do that, mathematically that means that I treat this quadratic operator as the operator plus times the expectation value. So if you look at it in this way, you clearly see that the frequency that before is going to be the detuning, the single particle detuning, is now modified by the presence of the other. Remember, SC is a measure of the projection of the block vector of the length of my spin along the z direction. So it tells me how many atoms are in the ground, how many atoms are in the excited state. So SC minus n½ is all the atoms down, plus n½ is all the atoms up. And this theta, this angle, I control by the first pulsarial dipole. The first transfer of atoms from the ground state is only controlled for the first pulsarial. So you can see immediately that we have a node to see whether the theory is really predicting, this collective spin model is predicting what we expect to be. Because we are saying this shift is going to be determined just linearly or depends on the excitation fraction. So this is the first experiment that they did at JILA and at NIST both, and they saw this very nicely linear dependence, very beautiful matching what the theory was predicting. So from that, there are two things that you can see from this plot. First, the nice agreement theory experiment. Second, a way to really extract what is the parameters that we characterize the interactions. And third, and this was used in the turbine clock, is there is a way to control and suppress the shift. So if we operate at this excitation fraction, then there is no shift, and then I can remove this problem in my clock. That's one way to see. So this is nice. It's really rewarding to see that this simple model works. But also you want to see what doesn't work, because mean field is an approximation. So how we can judge that there are correlations and some things that we are not accounted for in our theory. And the idea comes from the contrast. The contrast, on the contrary, if you try to model it by mean field theory, the mean field theory is going to predict the contrast is going to remain the same. It's just the particles are precessing at a different rate, but they don't change the length. It's just a rigid rotor. But on the contrary, quantum correlations, if you account for them, they tell you that you can shrink your block vector. And this is something that they should see in the experiment. So shrinking of the block vector, it can be associated with decoherence. So we have to be careful because, of course, there are other aspects that can cause decoherence that are not necessary interactions. So how to filter them out? Well, one consideration is that even at the mean field level, you can have a shrinkage of the block vector. Why? Even though for fixed number of atoms, we have just precession, in the experiment, they have a Poissonian distribution of pancakes. So you have many pancakes with different atoms in each pancake, a Poissonian distribution. So if you think about the block vector, one is precessing much faster when you have many atoms, and there are pancakes that have few number of atoms where the block vector is precessing very slow. But for the signal that this experiment measures, you have to sum over the signal of all the pancakes, and this can shrink your block vector, the different precession rates. So this is one. The second is that, as I mentioned, we have losses that also can decrease the length of your block vector. However, you at the mean field level is simple enough that you can account for all of these losses and the coherence from that. So that's what we did. So we wrote a theory, mean field theory, and tried to compare the contrast, the amplitude of the fringes versus time that was measured in the experiment as if with the mean field theory. So what we did is that because we knew that the density shift depended on the excitation fraction, we measured for different excitation fractions and compared with what we expect from the density shift. So we measured cases when there is just few atoms excited to cases when there are many atoms excited by the first pulse. So, and then you can see that we, as I mentioned, that the phasing from the different precession was a key factor. So here, for example, where the precession dominates, you can see that the mean field theory and the experiment agree very well. So this is kind of the classical regime. But if you look at here, at this point, when there is no precession from the density shift, then you expect it's only coming from losses from other processes, but you can see the very different behavior that the mean field theory predicts compared to what they was seen in the experiment. So here we thought quantum correlations were in action. And well, it's not always the case. For this particular system, we were able to account for the failure of mean field theory by developing a more sophisticated technique that in this particular case allow us to connect, go to the many body behavior by accounting the quantum corrections. And this is only because it's collective. So there are a few cases that when you can deal with that. But in this case, we account for the noise, initial noise, some quantum fluctuations. And you can see that using that theory, we were able to reproduce the experiment very nicely. So the message that I want to convey here at this point is to say, well, notice these are quantum corrections, even at microkelvin temperatures. So at least at the beginning, we have demonstrated that you can see quantum magnetism at microkelvin temperatures. So not necessarily we need very low nanokelvin temperature to see something. And when the fermions that are thought to be independent, they are collectively behaving. In BC, in superconductivity, that's something that happens. Fermions collectively behave. So this is not something as exotic as superconductivity, but still we are exploring a collective behavior of the fermions. So that's something very interesting. And let me say that, of course, the realization that you don't need very cold temperatures to see quantum magnetism has been explored, for example, by Paulette Gluck here at JQI. So with that, let me briefly move on by the last, yes, so I think how much time I have, like 5 minutes, 7 more minutes. I will tell you a little bit because I think it's really exciting. So far what I have told you is just the beginning. So far, we have not taken advantage of one key ingredient in alkaline air atoms, that is the nuclear spin. So far, all the experiments, because they wanted to use identical fermions, always polarize the nuclear spin to be one specific value. But there is a bunch of physics, a very broad arena of physics that we can explore by taking advantage of the nuclear spin. So this is what is going to be the next topic of my talk. And it's something that's remarkable, we just realized recently, is the fact that, well, if you look at an alkaline air atom, something unique happens in the lowest energy states, that is two external electrons can form a singlet. J equal to 0, they form a J equal to 0 state. If you have a single one, you can only have J equal to 1/2. But then, because J equal to 0 in these atoms, there is an intrinsic coupling between the electronic spin or the angular momentum of the electron and the nuclear spin, I. This is given by what is called hyperfine interactions. But in this case, because J equal to 0, there is not hyperfine. So that means that the nuclear spins and the electronic spin are independent, are decoupled. And this is key. It's subtle, but it's key because the electrons are the ones that determine the collisional properties of the atoms. That means that if the nuclears are isolated, they don't participate in the collisions. And actually, this gives rise to a new type of symmetry in your system, in your collision, a hidden symmetry that is SUN symmetry. It's a new type of group. It's kind of a rotation in a bigger space. Here, N is not the number of atoms that I was used to use, but N is equal to I plus 1. So N can be as large as 10 when I is equal to 9.5. It's large as 10 in strong, for example. So something that, well, let me explain. Something of the symmetry is that if you have, in quantum mechanics, if you have a symmetry, you associate this symmetry conservation laws. So something unique of this symmetry is that imposes large number of constraints and conservation laws in your collisions. And one of them, one particularly visible, for example, is the fact that you need to conserve the nuclear spin flavor. So if you have two atoms that collide that are red and blue, you cannot collide into purple and green. It's forbidden by the symmetry. You have to go out also red and blue. This doesn't happen in alkali atoms, that the atoms that are usually used for example, for BC. It's something new. So the question is, what type of possibilities such type of large N opens? And they are very interesting. And you can see that because, for example, well, SUN symmetry is known to have remarkable consequences in quantum mechanics. The simple example is the case of quarks. Quarks have color and they form a SU3 color. So now the atomic physics can allow us to start to think about the behavior of the quarks. The other is more on the theoretical point of view, but this is why SUN symmetry has been a dream for condensed matter theories. Because the problem of a strongly correlated system is that you don't have an expansion parameter. It's so complicated that there is no way to deal with the system. But if you have N large, you have 1 over N is small. So you have a handle, a perturbation parameter that you can use even in strongly correlated systems. So using this perturbation theory, when I arrived to the university, I talked with the condensed matter theorists and they were very excited about this actual implementation of SUN symmetry in realistic systems. This has been really an utopia. It's something that it was just a dream, something made up for helping the mathematics, but not actually found in systems. But now we have a system that really has this SUN with N large, and therefore we crank our calculations. And using that, we were able to predict that actually alkaline atoms in the ground state of a 2D lattice can form a new state of matter that is chiral spin liquid. That the frustration that is introduced by these conservation laws, so frustration is always a consequence, or there is a competition between having many degeneracies of possibilities with constraints. So this gives rise to a new type of state that is called chiral spin liquid, has been longly sought in condensed matter systems, not found. Strict evidence has not been found, but these kind of systems can be used for error-free quantum computation. So there is a direct application for topological phases that we can find here. And well, so of course, we have to see and look if this is the phases in the experiment. That's one possibility. The other possibility is that if you look at the behavior of condensed matter systems, there are 3 key ingredients that play a role. Charge of the electron, the spin of the electron, and the orbital degrees of freedom. And if you can think about one of the most exotic phenomena that we are looking for and we understand in solid state systems, like superconductivity, colloquial magnetoresistance, charge and orbital order in heavy fermions, all of those have in common the interplay between these 3. But it's so complicated, the interplay between those 3, that many open questions are still on. And for illustrating these open questions, I just look at a blog of condensed matter theories, and you see there is this nice cartoon that kind of summarizes the status. They say, we have shown that the recent unexplained behavior is different than the previous unexplained behavior. It's really complicated. It's really complicated. So the question is, can alkaline atoms provide an answer? Because they're really fully controllable. They have a spin, and it's SUN, so initially we have an additional possibility. They have orbital, we have these 2 very stable clock states. And well, we don't have charge, but we have mass, and this can play a role. So the question is, how much we will learn from that? And I'm really optimistic. I think we have seen recently evidence of the SUN symmetry in clock. In June experiments, I'm not going to enter in the details, but we have changed from 1 nuclear spin to many nuclear spins like this. and we have measured evidence, direct evidence of SUN symmetry. So this is the starting point. And I think there is a great vista ahead for alkaline atoms, and we are just starting. So we are here at the bottom when you have very low complexity, very high temperature. But there has been a lot of theoretical efforts, really a lot of theory that has been proposed. What is the beautiful things that we can accomplish and see if we explore this SUN symmetry in alkaline atoms, using clocks as a big starting point to see this phenomenon. So that concludes my talk today, and I want to thank you for your attention.
Beautiful, thank you very much. So do we have some questions for Ana Maria? Ah, there's one. I don't know, we do have microphones. We could, I can probably yell. Well, we have remote sites, and so it's better.
Right, okay. So do you think, if this work progresses, do you think maybe these quantum simulations will beat maybe nuclear physics to the punch at solving nucleon structure?
Well, I'm not sure. So I think there has been some proposals, so by Peter Soller, who is trying to explore dynamical gauge fields and trying to explore the physics that you find in quarks so trying to simulate this type of dynamical gauge fields. So this could be one point, but certainly something that would happen is the exploration between entangling between nuclear spins and electronic spins. So this is something that people have thought for quantum information. The nuclear spins, they do not talk with the rest of the world. Electronic spins do, but then we can do some gates in the nuclear spins and then decouple them or read them through the electronic degrees of freedom. So I don't know if this is the nuclear physics that you are thinking about, but there is something. There are clocks that are thought to operate with thorium in the nuclei of the thorium atoms, and this is also something, so how much we can use these nuclear spins for precision measurements. That could be another very interesting possibility. And we have deals, so Jun has shown that he can resolve the different nuclear spins transitions very accurately. So certainly there is possibilities to take advantage of the nuclear spin to explore them.
Okay, anyone else? There's a lot of satisfaction in the audience. So given that, let's thank our speaker again. Sorry. We have a nuclear physicist.
Since there are so few questions, I'll ask a dweeby one. Normally, I would think of triplet S as being metastable, but I noticed you showed triplet P, which I wouldn't normally think of as being metastable because it can decay to triplet S.
Yes. Well, so the triplet, so we have two transitions. The clock states are made from triplet P0 to 1s0. The transition from triplet P0 to 1s0 is both spin forbidden because you go triplet to singlet, and dipole forbidden because you go from j equal to 0 to j equal to 0. It's not completely forbidden, and that's why the clock operates. And the reason is that there are still hyperfine structures in the 3p levels that mixtures the 3p0 with the 1p1, with the 2p1, and this admixture is what gives actually transition. In bosonic isotopes, for example, like strontium-88, where there is no nuclear spin I and there is not real hyperfine interactions, this transition is completely forbidden, and in order to operate the clocks with the bosonic atoms, you have to apply some magnetic field that mixes the levels. So there is coupling, but
but I was asking about decay from the, you mentioned a very long lifetime, so I was asking about decay from the triplet P to the triplet S, not to the singlet S.
The triplet P to the triplet S, so the lowest energy states are 1s0 and the next energy state is 3p0.
Triplet S is a different principal quantum number, so it's higher than triplet P.
Oh, okay.
It's like 3s, 3p. 3s.
Oh, okay.
Yes, we are talking about the low energy levels of my atom, the lowest energy states, and these are the two that play a role, and these are the ones that are hundreds of seconds lifetime.
Okay, thank you.
Okay, last chance, no more standards? Okay, thank you very much, Ana. you.